Okay, thank you very much for the invitation to talk at this conference. I'm sorry I couldn't go in person, but hopefully another time. And yes, I'm going to talk about the recent paper we put out with Yiming Chen, which is just started his postdoc at Stanford, about spin statistics for black hole microstates. And please feel free to interrupt me whenever you have any question. Okay, so let me start with some motivation. So we want to understand the implications of the expectations of black holes being described by quantum systems and seen from the outside. And the most successful approach to analyzing gravity and producing answers consistent with this statement has been the gravitational path integral, Gibbons and Joaquin in its different forms, starting from things like the free energy, the Rita-Kayanagi formula, the page curve recently, has always succeeded in this sense. So the purpose of this talk is to understand the gravitational path integral in some setup that is, well, that at least hasn't been analyzed before. Okay, so the simplest and the first application was to compute the number of black hole microstates in the small g Newton limit in some ensemble, for example, as I said, the free energy thermal ensemble or the microcanonical entropy. And here these traces are not evident in gravity, but this is what we expect in a full theory of gravity. This should be the trace over some Hilbert space we are trying to understand. And from now on, when I write things like this, trace at fixed energy E, what I mean is with some energy window, but I will mostly work in classical approximation, so that will not be too important. Okay. Yes. So the question we want to address is how to compute from the gravitational path integral the distribution, at least in the small g Newton limit, of how these states distribute between whether they are bosonic or fermionic. And in principle, we could work in an ensemble where we fix the angular momentum or the spin and determine whether separately working when the spin is integer or half integer. Now, this requires including quantum effects in the gravitational path integral, which might not be impossible, but it's probably difficult, since otherwise, in the classical limit, all the charges of the black hole, in particular the angular momentum, are of order 1/g Newton. So it's something that is not easy to see in the classical approximation. So to extract this information, we will evaluate a different partition function with the insertion of -1 to the f. And again, we can work in the thermal ensemble or in the microcanonical, and the subscript spin on the entropy of the free energy means that it's a quantity with a -1 to the f insertion. And if we know both the quantities, these quantities with and without this insertion, then we know how the states are distributed, since this is an operator that assigns, well, from the Hilbert space point of view, it assigns 1 to bosonic state or -1 to fermionic states. From the gravitational path integral, it's a statement about the boundary conditions far away from the black hole, specifically fermions having been periodic around the time circle. We will analyze this problem in flat space, but this is more precise in the context of ADS-CFT, where this at least puts constraints on the partition function of a three-dimension of well, any dimensional conformal field theory in the presence of -1 to the f. So we want to understand what saddles contribute to this quantity. Two obvious ones are thermal ADS and the black hole, the original black hole that contributed to the original free energy without the -1 to the f. Thermal ADS is fine, it will contribute. The only difference is that when one includes low energy fluctuations, one have to keep in mind that fermions are periodic. But the black hole does not contribute because the time circle contracts, and this is not a compatible spin structure for the fermions. So in this talk, I will present a universal black hole solution that contributes to the partition function with a -1 to the f. This solution will be complex and will rotate, and we will study its properties. As an example of the type of results we are after, we will study this problem in ADS4, it should say, ADS4, sorry. And it puts the following constraint on 3D CFTs. So the the entropy without the -1 to the f grows at large energies as e to the 2/3. So this is what comes from an extensive behavior of the 3D partition function. And the new result is that this same entropy with the -1 to the f inserted grows slower with only power of 1/2. Well, yeah, so this is the type of results that will come from these black holes that we will study here. And finally, I will also analyze some wormhole contributions to this quantity. Now, before I start, let me relate relate the content of this talk to previous work. In particular, the talk that was given by Samir Murthy a couple of days ago is very relevant. So and I will repeat a little bit the motivation from the point of view of his talk. So from his point of view, microstate counting in string theory, which started a couple of decades ago, has always focused on, well, quantities that one can compute from the putative quantum mechanical dual, which is the index. So this is precisely the partition function with a -1 to the f. And usually one compares this index with the degeneracy, which is computed in gravity. Now, there are exceptions where you don't need to compute the index, such as 2D CFTs with the Cardi formula or numerical studies like BFSS, but okay. Other than those two cases, this is the way that microstate counting can be compared with gravity. But there wasn't really ever any comparison between the same quantities on gravity and quantum mechanics. It was always, you compute the index, you compute the degeneracy, and they happen to match, even though they didn't really have to a priori. So the new developments that Samir described is that we now understand how to compute the index from gravity. So now we have these two entries that we can really compute separately and compare. And of course, in most cases with supersymmetry, we find that the degeneracy and the index, at least at large n, they're the same, but in principle, they didn't have to. So it's good to, when we do these comparisons, to compare the same quantity on both sides, just in case. Okay, something that won't be important for this talk, but I just wanted to mention is that on the quantum mechanical side, the index can be computed exactly, at least in some cases, because it's invariant under the formations, the Hamiltonian. So an open question that is kind of also a future direction of the research that Samir described is, can we do also something exact in gravity now that we know how to compute the index? And there has been some progress in this direction, but okay. This was just to remind you of the setup. So when we apply this procedure to supersymmetric theories, as I said, we always find that the index is roughly the same as the degeneracy. Not always, but most cases. Now, in this talk, just to be clear, I want to explore how these two partition functions without or with the -1 to the f, how they are related in non-supersymmetric theories. So these will be quantities we will compute from gravity. We will see what they are, but they cannot be compared with, as far as I know, any example where one can do exact calculations on the quantum mechanics side. But anyways, we will analyze what are the predictions from gravity for these quantities. Okay. Is there any question about the motivation? Okay, so I will begin with black holes in flat space. These cases will be ill-defined. You will see why, but it's a little bit simpler than the cases in ADS. So I will explain more details here, and then it will make it easier to go over the examples in ADS. So we will consider a theory whose low energy action is Einstein gravity plus matter, and we will assume that the matter has at least some fermions, or that the theory overall has some fermionic states. And the most general black hole solution is a complexification in principle of the curved black hole. And here I wrote the metric just to have it, but of course you don't need to look at it too much. I assume that most people are familiar with it. Okay, so according to the Gibbons-Hawking prescription, if we want to compute the partition function and it will be useful to consider the more general case where we insert the angular velocity. If we want a prediction for this quantity, then this will tell us the boundary conditions, as I said before, far away from the black hole. And in particular, we will have this circle. The big circle is the thermal circle, and the smaller one is the spatial sphere. So in the case of four-dimensional flat space, it will be S1 cross S2. Then once we fix the boundary conditions appropriate for this ensemble, then we fill it up with all the smooth geometries we can, at least in the saddle point approximation. That solves the equation of motions. And in particular, this black hole has this topology where the thermal circle contracts at the horizon. And the horizon is located at R plus, which is related to the two parameters of the curved black hole E and A that I wrote here. Now, smoothness at the tip of the cigar requires imposing the following identification between, so TE is the Euclidean time and phi is the angle around the axis of rotation. So as we go around the thermal circle, we also need to rotate an amount I beta omega in this angle. So if we look at the T5 plane, we need to identify, well, first we have an identification of 2 pi around phi because this is an angular coordinate in the sphere. And then we also need to identify fields around this blue arrow, where as we go an amount beta in time, we shift an amount proportional to the angular velocity in the spatial coordinate. And then around this cycle specified by this blue arrow, the bosonic fields have to be periodic and the fermionic fields have to be anti-periodic, because this is the field that, this is the cycle that precisely contracts at the horizon and where the smoothness condition is coming from. Okay, and when we do this, we can find a relation between the inverse temperature and the angular velocity and the parameters of the curved black hole R plus and A, which is what I wrote here. And in principle, along this red arrow, which is along time only, without this shift in the angle, the boundary conditions are well, essentially, as the field goes around the time circle alone, all the fields will be multiplied by e to the beta omega j, where j is the generator of rotation. So the blue line has a simple boundary condition. The red line does not have a simple boundary condition. This will be important. Okay, so let's begin with the usual case of the partition function of the free energy without the -1 to the f. If we work at fixed temperature, we can set omega 0 to 0, which implies that A is 0. If we look at this formula. So then we are back to the usual Schwarzschild black hole. The Euclidean action, including the boundary terms, can be written in this way, in this ensemble. And this leads to the free energy being beta over 16 pi. This is just, I'm sorry, I'm working in units where G Newton is 1. That's why there is no G Newton. We can repeat the same calculation in an ensemble of fixed energy. We need to add the appropriate boundary terms. This leads to an Euclidean action given by this, so it's essentially the same without the beta E. And this gives the Bekenstein-Hawking 4 pi E square, which is the area of the Schwarzschild black hole divided by 4G Newton. Okay, so what fraction of this number of states are bosonic or fermionic? So to utilize the gravitational path integral, we evaluate this quantity that I introduced before. Now, as I said, the Schwarzschild black hole will not contribute anymore because it's singular. So the -1 to the f means that we want fermions to be periodic, and that's not compatible. So the procedure, and this is exactly the same one that Samir described, I applied more broadly. We'll find a new universal black hole solution by using the connection between the angular momentum and the statistics, and thinking of the -1 to the f as e to the 2 pi I j. And what this tells us is that we can extract this quantity by by tuning the angular velocity with the temperature such that the product of beta and omega is 2 pi I. And in principle, this could be for any, this should work for any sign. So why does this make the fermions be periodic around the time circle? So here I draw the same diagram, but for the case where I beta omega is 2 pi. So the contractible circle again is this blue arrow where the fermions are anti-periodic, but now fermions are also anti-periodic around this phi circle that goes from 0 to 2 pi, because this is a circle in a sphere that is contractible, so fermions have to be antiperiodic there for sure. So if fermions are antiperiodic in the blue line and they're antiperiodic from here to here, that implies that the fermions will be periodic, and also the boson will be periodic along the cycle identified by the red arrow. So then this solution is totally smooth in this sense because, well, as I said, the spatial one is antiperiodic, always contractible. The blue one is antiperiodic, and because it's contractible at the horizon. The red one is periodic, but it's not a cycle that contracts inside the black hole geometry. So then there is no inconsistency with fermions being periodic in this circle. And again, well, I already said it, but this idea was used in these papers that Samir also mentioned, but for some reason it was only applied exclusively for supersymmetric black holes in supergravity. So I want to generalize. So one comment, this one will not be very important at the classical limit, but I wanted to make it. So I said when I write this relation, I could take in principle either sign, they will both work. But even moreover, of course, this relation is valid regardless of my choice of direction for J. So here J is some arbitrary direction that I pick. But in principle, if I take the spin around any direction, this relation will still be true. And there's actually a moduli space of solutions for the black hole specified by the direction. And this has to be integrated over. So there is this vector n is supposed to indicate the direction of rotation, so we can integrate over all possible directions. And this is not important. So this talk we will restrict to the classical limit. So this is something only important at the quantum mechanical level. Well, something that is important is that this modular space is compact, because otherwise one could be worried that this can lead to some divergences. But okay, this was analyzed in the supersymmetric context here, and also by more detail by Sen recently.
What happens if you use 6 pi ij or 10 pi ij?
Yeah, so that has to sum over as they have to be summed over as well.
Other ones have subleading contributions?
Almost. I mean, that's an open question. I don't know. So yeah, I guess what you're saying is that here this boundary condition is really only relevant modulo 4 pi I, essentially. But the black hole depends on the real value of omega, the way you fill up the geometry. So yeah, then you have to sum over these shifts. And the expectation, I don't remember this case in particular, the expectation would be that these are subleading, but there are cases where it's not. So then there should be some argument telling you that those cells should not be included. Maybe along the lines of your criterion. But yeah, I think it's an open question to understand that better. So here I'm restricting to the what I expect to be the dominant one, where we take the minimal value. But yeah, that's an open question. Thanks. Okay, so yeah, the reason why I was bringing it up is because this at least explains why we can take either sign. So picking the plus or the minus are just two orientations of the. There are two specific points of this modular space. For concreteness, I would pick the plus sign, but it's not important. Okay, anyway, so going back to the black hole, we have two parameters, R plus and A. So the first thing we can do is determine A by the condition that beta omega is equal to 2 pi I. If I use the explicit formulas, then this is what I get. But if I set this ratio to 1, I find the solution that A, here I remove the factor of I just to make things as real as possible. This both A will be equal to plus or minus R plus. And this has a problem because it leads to beta being exactly 0 for any value of R plus. So this is weird. So instead, this is an issue that will be regulated in ADS. Instead, we set beta omega over 2 pi I to be 1 minus epsilon. And we find a new solution where as epsilon goes to 0, beta is tunable, but it requires an R plus that diverges. Yeah, so R plus is going to infinity as epsilon goes to 0, but other than that, we can keep beta fixed. the energy is fixed, the charges are fixed. Also, the invariants made out of the curvatures are finite in this large R plus limit. So this tells us that maybe it's not too crazy to include this saddle. But again, as I said, this will go away in ADS. Okay. So the action of the rotating black hole contributing to this quantity F spin is now takes this value for any epsilon, and when we send epsilon to 0, we get beta over 8 pi. And you should compare this with the free energy without the -1 to the F, which is beta over 16 pi. So how can we interpret this? We can consider the microcanonical ensemble instead and fixed energy. Then R plus will be given as some function of the energy, but as I said, it will still diverge. And when we compute the action in this ensemble, so again, well, anyways, if you compute including the boundary term, the action, you get that can be written in general in this form. And here the entropy will not be with the -1 to the F. It's not only the area over 4G Newton, it also gets a contribution from this term. And something similar happened in Samir's talk. But okay, the answer ends up being 2 pi E squared. And this is half of the, well, to remind you, the entropy in my conventions of the Schwarzschild black hole was 4 pi E squared. So the entropy of these black holes with the -1 to the F insertion is half of the entropy without it. And to remind you, this is the definition of what I'm calling S-spin. Okay. So this is a reasonable, or at least I consider it to be a reasonable answer. It says that the sum of the bosonic and fermionic black holes and their difference, so the sum grows as e to the s, which I call L. If that's the case, then the difference between bosonic and fermionics grows as the square root of L. One can interpret this as saying that from the whole set of black hole microstates, they are randomly distributed between bosonic and fermionic, because this is a square root. And this is, I think, more satisfactory than a non-supersymmetric black hole, where usually all the states have the same statistics. I think that's too fine-tuned, and indeed the same procedure that gives that answer for the supersymmetric case predicts something more reasonable for the non-supersymmetric case.
So,
yeah.
So this solution you're looking at in this limit is R plus goes to infinity, so the horizon size is going to infinity?
Yeah, that's why I said it's weird, but this will go away in ADS if it bothers you. Just the formulas are simpler to begin with in flat space. But yes, the size of the horizon goes to infinity, but all the physical quantities like the entropy or the free energy remain finite in this limit.
Do you understand what the physics of that is?
No, I don't really know. Yeah.
Okay.
No, I don't know. Yeah. Yeah, I thought about it, but I'm not. I don't have any satisfactory thing to say about it. It's just, yeah. As far as I know, it's the way it is. Yeah. Thanks.
Okay.
Is there any other question in the meantime? Okay. So to go back to the original approach I said of fixing the spin and being careful about whether it's integer or half integer, a naive way to compute this quantity would be to sum over J and then evaluate e to the entropy as a function of E and J. So this is the entropy of the curved black hole. And then I could just put e to the 2 pi I J by hand. Now this, and then evaluate this sum. Now this sum in the large energy limit, it does reproduce this factor of 1/2. But I don't think this calculation is justified because in principle, there could be other phases coming from one loop determinants that we wouldn't be capturing by. Here I'm assuming that everything is real except everything, yes. Nothing has a phase except this -1 to the F that I'm inserting. So this is naive, but it gives the right answer, consistent with. So it also supports the idea that we should include this complex black hole in the gravitational path integral, even though it looks weird because of this behavior about R plus. Okay, now I will go over the charge case. So we can repeat the same calculation for Einstein-Maxwell. Now we have a Kerr-Newman black hole. These are the relations. These are the potentials as a function of the parameters of the solutions that come from smoothness. The parameters are R plus and A, but now we have Q. And the entropy without the -1 to the F has this function, is this function of the energy and the charge. Only for energy is bigger than Q, which is the extremality bound. So now we can repeat the same procedure and consider the entropy with the insertion of -1 to the F. And now we introduce this bold A, and the condition of omega tells me that A has to be R plus minus Q. And then we need to solve R plus as a function of beta. And this has a finite solution, but it has the problem that if we compute the free energy, we get this answer, pi Q squared minus beta Q. This solution is precisely the one that appeared in Samir's talk, at least for pure n equals 2 supergravity, without vector fields or scalars. In the context of this talk, this solution is too restrictive because it only contributes, for example, in the macrocanonical, it only contributes states with E equals Q. And this makes a lot of sense, again, from the point of view of supergravity, but in general, we could compute the trace of -1 to the F at any energy. And it doesn't have to cancel in general. Okay, so again, what we find is that we need to regulate this, the way we take this limit, and again, this is removed in ADS4, in general in ADS. So beta omega will be 2 pi I up to 1 minus epsilon, and when we send epsilon to 0, we find a new solution that with again R plus that is divergent. And the reason why this happens is because it's a polynomial equation for R plus as a function of beta, and when you send epsilon to 0, the order of the polynomial changes, and then that's where these solutions appear and disappear. But okay, anyways, we can compute the free energy and we get this answer. Well, this solution is not supersymmetric if we embed it in supergravity, and it does not contribute to anything of what Samir discussed. And again, we can interpret this a bit more transparent, in a more transparent way by working in the microcanonical ensemble. And then we get that the entropy with the insertion of -1 to the F is this function of energy and charge. So this is a little different than the answer without the -1 to the F, which was this. So for example, this is a plot of how the ratio between the entropy with and without the -1 to the F looks like as a function of Q over E. So at small charges, we get the uncharged answer, the 1/2. I don't know if you can see the numbers. As you increase the charge or you lower the energy, the ratio goes from 1/2 to all the way to 1, which is the supersymmetric, or the answer you will get if you embed it in the supersymmetric theory. Okay, now of course, if you don't have supersymmetry, so this limit will be the extremal limit. Extremal black holes are quite subtle. So unless you do have supersymmetry, I wouldn't interpret it as saying that extremal black holes are all bosonic without supersymmetry, but at least at the classical level, this curve, this is the behavior of this quantity. Okay, so now I will repeat the same for ADS. And again, this is a better question, because if we ask this question in ADS, we can put constraints on the high energy spectrums of 3D CFTs. So a reasonable low energy theory that arises from some examples in string theory is Einstein-Maxwell in ADS4 plus matter. And here the motional black hole is the ADS version of generalization of the Kerr-Newman black hole. So again, it depends on R plus, A, and Q, and also now the ADS length. I'm not gonna go over all these details. This is probably simple algebra you're all familiar with. But imposing that the Euclidean section of this solution is smooth, it relates again the potentials with the parameters R plus and A. And the charges are related to this parameter as in this way. So, well, M is some function of R plus, A is proportional to the angular momentum, and little q is proportional to the charge. For simplicity, I will consider the uncharged case, but one can generalize it easily, straightforward way. Okay. First, let me remind you how the partition function without the -1 to the f looks like. So we set omega equals 0. We compute the thermal partition function. Now the black hole solution only contributes, only wins over the thermal ADS contribution for temperatures that are higher than the Joaquin page transition. So we will focus on the high temperature limit. The on-shell action can be rewritten in this way again. And this gives the following partition function in general, which in the large temperature limit goes as 1 over beta squared. And this is an answer that is consistent with an extensive result at high temperatures for the partition function of a 3D CFT. Yes. In the macrocanonical ensemble, we can use the same black hole, but with different boundary conditions, which change the action a little bit, and compute the trace of 1 over a fixed E ensemble with some window. And the answer for the entropy is again, well, some complicated function of E that at large energies goes as E to the 2/3, which, as I said before. And well, this is the case that I was mentioning in the introduction. So this is the Laplace transform of that thermal free energy that I wrote in the previous slide. Okay, so after this, reviewing this, then what is the gravity prediction for the spread of these microstates between bosons and fermions? Now we do the same. We implement the -1 to the f as picking a particular angular velocity. Now we find two solutions. One where A is equal to R plus. This solution sets beta equals 0 and energy equals 0. So this is the analog of the finite but bad solution in flat space, still there in ADS. But in ADS, there is a new solution that appears, which is, here it appears without the need to regulate the beta omega going to 2 pi I limit. It's just there. And this solution does lead to a variable beta temperature or energy. So this is a good solution. So we can take this A and plug it in the formula for either beta or E, and this is what we get. So now what we have to do is if we work in the thermal ensemble, we will solve for R plus as a function of beta. And if we work in the microcanonical ensemble, we will solve for R plus as a function of E. And these are high order polynomials, so they will have a bunch of solutions, and it's important. Or one of the problems is also to decide which ones to keep and which one to discard. Okay. In the thermal ensemble, there are 4 solutions. It's a 4th order polynomial. We found numerically that for any positive value of beta and L, well, this can probably we can probably show it analytically, but well, anyways, you can also just play around with solving these equations. There are always 2 real solutions and 1 pair of complex conjugated solutions, at least for real beta and L. The solutions are all finite, so R plus is finite. The solution, I mean, R plus is a function of beta. R plus is finite. And in all cases, we find that the real value of the action is positive. So in all cases, thermal ADS gives the dominant contribution. In particular, another interesting property is, let's say that we work in an ensemble, in a thermal ensemble, but where we fix some charge. And we can take that charge to be small, so it doesn't change these answers too much. Then the free energy with the -1 to the f has this behavior as 1 over beta with some numerical coefficient that's not too important. But the thing I wanted to stress is that this violates the extensivity at high temperatures that the free energy without the -1 to the f does have. This I think it's interesting because it connects perhaps with some recent paper of Benjamin, Simons-Duffin, and Oguri about the thermal effective field theory. So this would violate the effective field theory when you insert the -1 to the f. I don't think the effective field theory is wrong. Probably what happens is that this behavior would tell you that there has to be some other solution that is more dominant that is not this universal black hole. But this is not something we studied in our paper. We focused on the black hole behavior mostly. Okay, so one conclusion is that there are no Hawking phase transitions when you insert -1 to the F. So if you don't do it, then at small temperatures you have thermal ADS, but at high temperatures you have the ADS black hole, and this is well, if we were doing it in ADS5, it would be the confinement-deconfinement transition in the dual CFT. But when you insert the -1 to the F, the black hole is always subleading, and there is no phase transition as you go above the Hawking page temperature. Well, this I already said. So, and similar behavior or this lack of phase transition in the trace of -1 to the F was also found for adjoint QCD in 4 dimensions in this paper, and well, it's nice to see it from gravity. So it is instructive to consider also the macrocanonical entropy. Now we need to solve R plus as a function of the energy, and now it gets more complicated because this is a 8th order polynomial for R plus, and we find 8 pairs for all positive energies and positive real Ls. We find 4 pairs of complex conjugated solutions. 2 pairs have positive real part of the action, so they are small. And the other 2 pairs have negative real part of the action. So this, even though the black hole doesn't dominate the thermal ensemble, it does have contributions that grow, or that grow with the energy in the macrocanonical. Okay, so we focus on these 2 pairs of solutions. Oh, sorry, this should be a plus minus. These solutions, there are the solution 1 and the solution 2, they have different real parts of the action, and the first solution has a smaller real part of the action. So naively, we would think that the solution 1 would be the dominant one, but we find numerically that for any value of the energy, the real part of R plus is always negative, and this violates this criterion that I mentioned before by Witten based on Konciewicz-Siegel previous paper. It also does not have a nice flat space limit, so we propose that this solution should be discarded. Of course, we don't have any rigorous proof of this. It's just as much as there is no non-perturbative definition of the path integral without I don't know, going to string theory or to the dual CFT. But anyways, the behavior of this saddle is very strange, and so we propose that it should not be included. So the conclusion is that we propose that the second solution should be the one that is included, even though it's not the most dominant. Another funny thing is that we find a pair of complex conjugated solutions, so they can interfere in the path integral. So then there will be a sum of 2 terms. We didn't compute the one loop correction, but we know because the solutions are related by I going to -I, they will be complex conjugated of each other, and also the actions are complex conjugated of each other. So we propose that you should sum over them, and the sum is given by the second line here. So the imaginary part of the action is given some very rapid oscillation on the overall partition function with the -1 to the F. The argument of this phase, we don't know. We need to know the one loop determinant. It is important, but we didn't compute it. But we still contrast the frequency of as coming from the imaginary part of I. So this is similar to what happens in the WKB approximation, for example. And then the real part of the action gives the leading order envelope of this partition function, function of the energy. And then the absolute value of the one loop correction, we also didn't compute it, but it will be some small correction to this. So the most important part here that we didn't evaluate was the phase of the one loop determinant. Okay, so this can be done. So I just mentioned some facts about the solutions, but this can be done analytically in the large energy limit. Now, something funny about the large energy limit is that usually you achieve large energy by taking large R plus. Here, if you take large R plus, the energy goes to 0 because there are more powers of R plus in the denominator than in the numerator. So instead, the way to get large energy is to find the roots of the denominator. So what are the R stars where the denominator vanishes? There are 4 pairs. And then we can find R plus as a small fluctuation around this R star solution. So this way, what I just said, the general behavior that I just mentioned before, you can be seen analytically by solving these equations at large energy or small delta R. So doing this and evaluating the on-shell action gives this action for the solution we want to keep. Oh, sorry, here it should say I2, not I1. Anyways, so we find that the real part grows as the square root of E with some coefficient C that 3.81 is some numerical factor, not too important. Just the only important thing is that it's positive, an order 1. So this gives the growth of the energy, the growth with the energy of the trace of -1 to the F, fixed energy. And then we have the imaginary part that tells us the frequency of oscillation of the same quantity. So this is roughly how the partition the trace of -1 to the F looks like. So on the right, we have the macrocanonical. The blue line, this is not to scale, it's just to show you roughly qualitatively how it works. The black line is the envelope that grows as e to the square root E, and the blue line is the rapid fluctuations coming from the imaginary part of the action. And on the left, I'm showing the ratio between this quantity and between the contribution to S spin from the real part of the action and the total entropy without the -1 to the F. So it starts at 1/2, which is the flat space result, and then it goes up and then it goes down at large energies, and it actually goes to 0, but very slowly. And we take this as an explanation of why this black hole doesn't dominate in the thermal ensemble, because even though the trace of -1 to the F grows on average, there are large fluctuations that are visible in gravity, but they produce the interpretation we give is that this produces a large cancellation when we take a thermal trace with the -1 to the F. So that's why even though this entropy grows with the energy, it's not visible in the thermal ensemble where thermal ADS is the saddle for all temperatures.
Can I ask a question?
Yes, please.
I mean, I'm not sure if it's the right place to ask the question, but I mean, your calculation is so universal. So suppose that your CFT3 dual is made of completely bosonic fields only. Then -1 to the F will be identity, and where should your arguments be corrected?
Yeah. So actually, I have a slide about that, but I can give you a quick answer that is related to what Edward asked before. So the reason why you can that you should sum over these shifts of 4 pi I and beta omega in the rank canonical is because there are changes in omega that you cannot probe by anything far away. So they're indistinguishable as boundary conditions for the path integral, because any probe will have integer or half integer spin. But if you have only integer spin instead of half integer, then beta omega is defined up to 2 pi I instead of 4 pi I. And then this saddle that I'm evaluating here will contribute to the same observable.
But how would the semi-classical gravity know it? I mean, you're just using Einstein-Hilbert plus. I mean, to do you just impose it by hand or what?
Well, yes, I guess that's a way to say it. Well, when you say it's gravity, for example, you could say if I sum over metrics, but do I also include sum over spin structures or not? So that's also a choice you can make in gravity as a specification of your theory of gravity. And then if you don't sum over spin structures, then probably you would take the 2 pi I identification, and if you do, then you have to look at the 4 pi identification.
Yeah, but
this is perhaps more clear if you think about an analogous case, which is with the electromagnetic gauge field. There you have a similar sum over shift where you shift the chemical potential by integer fluxes. And the coefficient of that integer flux, it depends on what is the size of the let's say you have electromagnetism, what is the size of the U1 group? For example, is it U1 or is it R? And that is extra information you have to give in the bulk as well as in the boundary.
Right. So in a sense, it's similar to Edward Witten's question that 4 pi I periodicity was not manifestly visible in, 2 pi, 6 pi, 10 pi. I mean, it's a kind of similar question you're saying.
Yeah, but yes, and I'm saying that that's a choice you can make from the point of view purely of the bulk.
Yeah.
That is part of the specification of your gravity theory.
Okay.
Or in the electromagnetic case that I mentioned, is a specification of what is the actual group of the electromagnetic field. Is it U1 or R that changed these shifts?
Then it means that the 2 pi I calculation you did is just forbidden. If you know this all.
No, it means that it adds up to the partition function with omega equals 0. It's a subleading contribution to that.
But it's anyway subleading. Okay.
Yeah, because they both have the same boundary conditions.
Oh yeah. So 2 pi I, 4 pi I, 6 pi I can all be added up to see hopefully the 2 pi I periodicity of omega or something.
Sorry, if you have fermions, you have to do 2 pi I.
I mean, let's say without fermions. Without fermions.
Yeah, you have to add them all, including the 0.
Okay, I see.
So you are really computing the same. You are computing two quantities that are, from the point of view of your boundary conditions at infinity, are indistinguishable.
Okay, thank you.
Yeah, so you have to make that choice in both sides of the duality.
Okay, thank you very much.
Yeah, okay. Thanks for the question. What time did it start? Sorry, I forgot. Was it?
Wait, you still have 10 minutes more.
10 minutes. Okay.
12 minutes.
12 minutes. Okay. Okay. So maybe I will go a little fast. Okay. So in the next couple of slides, I wanted to describe the case of ADS5. So the procedure by now should be straightforward. So I've just pointed out the main features. So we can consider again Einstein-Maxwell. So the black hole is more complicated. This is the solution with all these parameters. So now the difference is that the spatial boundary is S3 with this parameterized by these triangles in the solution. So the solution without charge has energy and has two angular momenta around the two planes of rotation. Smoothness, again, relates the potentials to the parameter of the solutions. A is like the A of curve, but associated to J1, and B is associated to J2. And R plus is the location of the horizon. The thermal free energy without the -1 to the F goes as 1 over beta cubed, and the energy grows as 3/4. This is the usual extensive behavior. Now, the only comment I wanted to make, the reason why I bring this up is because, okay, now there is a question of how do we implement the -1 to the F. So J1 is equal to J2 modulo the integers. So a fermion has half integer spin around, if you have a fermion, it's half integer spin around J1 or J2, or a boson has integer spin around either. So therefore, we should pick either e to the 2 pi I J1 or e to the 2 pi I J2. Now, there is a different notion of fermion number one can define that uses the fact that the rotation group of the S3 decomposes into the product of two SU2s. And then you can use the generator of the left moving, or the left, I call it left, okay, I guess, of the left SU2 and the right SU2. And this JL and J right are linear combinations of the J1 and J2. But I just wanted to emphasize that this will give different notions of these three operators are not all the same. And when we talk about the statistics of the states, we want to compute this one. But of course, one can apply the same procedure to inserting this -1 to the FL or FR, but we just won't do it. And the conclusion is the same as ADS4 qualitatively. So we find that even though there is a Joaquin phase transition in the partition function, there is no phase transition for the trace of -1 to the F, and thermal ADS always dominates. The only difference here is that now when we compute the microcanonical answer, it does not grow with the energy. So this answer where S spin grows as square root E in ADS4, this doesn't happen in ADS5. The coefficient of that power of energy that we get is negative. So this means that the black hole doesn't contribute a large amount in this ensemble either. Okay, and finally we have black holes in ADS3. Again, we implement the fermion parity operator as -1 to the F being e to the 2 pi I j, where j is the generator of rotations on the spatial boundary of ADS3. And I just wanted to emphasize again, which is actually related to the previous point, that this is not what one could call the elliptic genus for a supersymmetric theory. That usually involves the presence of a gauge field, and the -1 to the F is actually, well, there is a relation like this, but J is not the generator of rotation in the spatial circle, it's instead the R symmetry charge of associated to this gauge field that is present. So again, that's a different observable. One can compute it. We computed it in the paper with Iliesu and Kologlu on this, but in this paper we compute the trace of -1 to the F defined in this way. And let me be a little quick because I don't have too much time. But essentially the answer is that in the microcanonical it's subleading. Sorry, I'm lost. Okay, here. If the free energy with the insertion is subleading, thermal ADS3 always contributes. But now if we compute it in the microcanonical ensemble, the entropy is again a fraction. So this is similar to the flat space result. It's a fraction of the entropy without the -1 to the F. Only that now the fraction is 1 over square root 2 instead of 1 over 2. And another difference is that we in ADS3 we again also have these rapid oscillations from this interference of the two saddles. Okay, in the last couple of minutes, I will try to go quickly over the wormholes contributions. So far we extracted the universal black hole contribution to this quantity, which we can take to be the number of states with the -1 to the F. But we can ask what happens if we consider correlators of these multiple insertions of this density of states, and this quantity to leading order will be a product of these black holes, but it will get subleading contributions from wormholes. We will consider a related quantity, which is the spectral form factor, but with insertion of -1 to the F as a function of time t. So the spectral form factor is this quantity without the -1 to the F. This is a review slide. So this quantity to leading order, if you have the product of the two black holes, it decays because you cannot see the discreteness of the spectrum to this order, so it decays with time. And the leading order wormhole that was found by Seth Schenker and Stanford is the double cone, which you can construct universally. And what I mean by universal is that if you give me the original black hole, I can just draw it in Lorentzian signature, identify the blue and the red line, the green and the red line by propagation by a time t, and create this cone. This cone is actually smooth if you analytically continue around the tip. And this gives the leading order contribution at late times to the spectral form factor. The action of this saddle vanishes, and the one loop determinant grows with time with a particular coefficient. And this is the answer. And this integral over energies is divergent, but it can be made finite if you work in a microcanonical ensemble where, so this integral over E will be given by the width of the energy window of your microcanonical ensemble. So it's useful to consider first as a toy model as a warm-up the case with a gauge field, so we can compute the spectral form factor with the chemical potential. This means we start with the Rhizome-Northron black hole, let's say, if we want to do it in flat space. And mu is specified through the holonomy of this gauge field at the boundaries. Now, the gauge potential for the Rhizome-Northron black hole has this form. So this mu is fixed by the boundary condition, and Q, usually in the usual black hole, Q is fixed as a function of mu by demanding that the gauge field is smooth at the tip of the horizon. But now in this double cone, if you construct it from Reiser-Nordstrom, in the actual contour that Sachin and Stanford proposed, where the time circle never shrinks, there is actually no restriction on Q. There is no smoothness condition that specifies Q as a function of mu. So all Q are good, smooth solutions that contribute to this quantity. So yeah, so the on-shell action in this case ends up being the same, the full answer, in particular the on-shell action vanishes, and the full answer coming from the one loop determinant is the same T over 2 pi. We have the window over energies, and we also have an integral over charges, which is regularized by working on a window, fixed charge up to some window. Now, charge should be integer, and the way you see it is by these integer shifts that I mentioned before. Yeah. So now we can do the same, and we can do the same with the -1 to the f, and the answer is very simple. So the -1 to the f can be thought of as some particular value of omega, but now there is no constraint determining either the energy of the angular or the angular momentum of the black hole, because there is no circle that contracts. So the insertion of -1 to the f doesn't affect anything other than the boundary conditions for matter field fluctuations, which now will be periodic if they are fermions. But matter fluctuations are suppressed in the large time limit. This behavior here comes only from the gravity mode. And this was in the original paper, but it has been explained in more detail in follow-ups by Ba, Chen, Maldacena, and some work in progress by Yiming Chen, Victor Ivan, Maldacena. So the main conclusion is that when you put the facts of the previous slides together, the spectral form factor with or without the -1 to the f is identical. The difference between these two quantities is only relevant at early times, but at late times, they have the same coefficient of this ramp. They both have the same ramp and with the same coefficient. Now I don't have too much time, but I will skip this. But let me just say it in words. What I wanted to do in the next slides was to explain, to give a random matrix ensemble interpretation of why these two quantities should be the same. If anyone is interested, I can mention it, but okay, I will skip it because of time. So let me conclude. So we show how to compute the partition function with insertions of -1 to the f, and how to do it using the gravitational path integral. In particular, we study universal black hole saddle, and we analyze contributions from wormholes. Now, the first thing I was going to mention is the puzzle. What if I want to make a theory with only bosonic states? So I will skip it because I already answered it. The second thing is that we study universal black hole contribution, but there could be other solutions. For example, one could have a defect at the horizon where far away the solution looks like a black hole, but then when you go close to the horizon, the thermal circles stop shrinking and the angular directions end up shrinking. This will allow periodic fermions, and it will contribute to the trace of -1 to the f, but we have some comments about how to construct these solutions in the paper, but we didn't do it in much detail. And finally, well, I wanted to emphasize the fact that if our black hole is the dominant one, then it violates the thermal effective field theory that was explored in this paper. And I think it might be interesting to understand how this issue is resolved. Okay, thank you very much for your attention.